are going to be talking about combined dimensions. Now previously, you guys went through and defined your three fundamental dimensions. These are mass, length, and time. Also previously, you started talking about combined dimensions, but only those using 2 out of the 3. So for example, velocity is a length per a time, or density is a mass per a cubic length. Today, we're going to look at 3 combined dimensions that use all 3 of our fundamental dimensions. Now the first is force. You have a picture of this in your head because in the US system of units, force is actually the fundamental unit instead of mass. It's weird, I know, we just get over it as engineers. So force, we're pushing on something. In the US we measure this in pounds force. In the SI system, force instead is measured in newtons. Newtons is a derived unit. So this actually gets us to, well, what are these combined dimensions for force? Force, from physics, is defined as a mass that is accelerated. So we know mass, and we previously talked about acceleration. That is a length per time squared. So force is a mass times a length divided by a time squared. That actually gives us the breakdown of how we get to newtons in our SI system. The fundamental unit there for mass, kilograms, times our fundamental unit of length, meters, divided by our time squared, or seconds squared. So we used mass, we used length, and we used time to give us force. Pushing on something, pulling on something, we have an idea of what a pound is. Then we have energy. Now energy is also defined as work if we're talking about this in a physics context, because this we can say is force over a distance. So energy, which I'll write as E, force times a length. I can expand that out since I know what force is. So I have a mass times length squared, divided by time squared. Looks a little funny, but it happens. Now in the US unit system, we just kind of start combining things. Our standard unit for energy, we have pounds force times our standard unit of distance, feet. However, in the SI unit system, we define a new combined unit for representing energy. This is what we call a joule, which is, by definition, a force measured in newtons times our standard distance, which is in meters. Now our third combined unit is taking energy one step further. It's saying how fast are you using energy? How fast is energy being created, perhaps? So we have power, and this is a energy per time. Again, we can combine it all into just our 3 fundamental fundamental dimensions, mass, length, and time. So in this case, we have a mass times a length squared divided by a time cubed. When we think about power, in the US we often think about things in horsepower, which is actually derived, a little bit of conversion factor happening, from what is technically our standard unit, which in the US is pounds force times feet divided by seconds. Yeah, it's weird, I know. I like SI. Yay, environmental engineering. In the SI unit system, though, they produce another combined unit to represent power for us, and this is what we call a watt. A watt, by definition, is a joule per second. Now, you might be more familiar with the unit of watt than you think you are. If you have ever looked at the energy bill, the power bill for your house, they're probably measuring your power consumption in kilowatts per hour, perhaps. So maybe not quite as brand new as you thought. Now, one application for just thinking about the units in a problem is when you get an equation that you haven't really seen before. If it's a theoretical equation, the units will be able to cancel out for you so that you can determine the dimension or the units of your answer. So over here we have an equation, sort of mystery equation, from our FE reference handbook. This is the standard testing practice guide for the fundamentals of engineering exam, what you'll need to take in order to become a professional licensed engineer in the US. Now, they've also given us a picture so we can start figuring out what some of the dimensions are on the variables on the right-hand side. So I can think about what is happening in this equation, use my picture, and determine what the units or the dimension that I would expect to see in WB is. Now, in my equation, 2 pi, that's just a number. So this is going to be unitless. Nothing goes in there. F, if I look at my picture, or I just think about what we already defined F is a force. So this is going to be mass times length per time squared. R, from the picture, is a distance, so that is a length unit. And then finally we have n. N is potentially the new variable in this for you. N is what we call a rotational speed or a rotational velocity. And that actually comes just in units of per time. So when I combine my units across, in the numerator I have mass, length, and length. So mass times length squared. In the denominator I have t squared times t, or t cubed. Combining these dimensions, looking at my reference values, this means I would expect that WB is a power. In this case, it is. This is actually the equation for braking power. Whenever you step on your brakes in your car, this is telling you how much power the brake is exerting. All right, good luck on your homework problem.